is a dimension into the board, so that's no controversy. And now with a little difference in the angle, essentially I'm asking, what is this surface area? Can someone use trigonometry and help me with that? I have a height h, I have a right angle triangle with an angle of 60 degrees. The area I wanted is the hypotenuse of this triangle. So what would that h, be careful now. Sine, cosine. This is, the angle is different than the diagram on the left, so don't look at the diagram on the left now. Focus on the diagram of this right angle triangle that I just draw. I want a hypotenuse which is longer than the height h. H divided by sine 60. Very good. In feet. This is not easy to see, but back home when you're at more leisure, you can check that. Am I done? This is final exam in a week and a half, 2 weeks. Am I done? I'm missing a G sub C. Remember my 3 strike? You are out. Coming? So it's coming to that now. Okay? Make sure you don't miss the G sub C. So with all that, it's just algebra. You do it, what left? After all the calculation. It's a h squared type expression for the net force due to the fact that you have this average pressure and the area, both of which involve the height h. All right? So, that all done and behind me. Now I'm going to do the moment force about M at point B, which must be 0 for the 2 counteracting forces, one clockwise and one counterclockwise. Force is 360 h squared due to water. Now I need my location. I have a rotated pressure prism. Where is this center of pressure? No one has a clue? No one has a clue? Anyone else? You're confused because now the prism has been rotated. Let me get you oriented. Where is the center of pressure for this upright triangle? 130. This is h divided by 3. Now I have the angle prism rotated. Where is the center of pressure? 1/3 from the base. H divided by 3. H is the height of the water. No, sorry. Yeah. Let me be careful. This is 1/3 from base, such that, and this is something I want you to study at home. So the moment arm, which is perpendicular to that force, is h divided by sine 60. It's not transparent, it's not something you click and say, oh yeah, I know. It may be something you have to sit there at home and go through it just to make sure that nothing is done incorrectly in my expression here. It is 1/3, but 1/3 from what? That height h has changed, so it's h divided by sine 60. All right? So now I have an equation in h cubed. You solve that, and h becomes about 10 feet. Anything beyond that, gate will fall and the water will spill over. Questions? Questions? Your homework is very similar with a slight twist, and then I'm going to give you just a quick 2-minute break so that I can erase the board. It's where, again, you have a cable with tension holding a gauge, water on this side, and the other complexity added is the weight of the gauge cannot be neglected. You have to also include the weight of the gauge. And with other information given in the problem, you are asked to find the tension in this cable. Can you do it? Yeah, I hope. I hope. The only thing added is the weight of the gauge. But all this will come into play, how you draw a pressure prism, what happens when you rotate it, how the area change, etc., will be needed. So I'll give you a 2-minute break so I can erase the board, and then when we come back, we're going to dive into the differential equation.
What was that? Did you bring your house, or was it for the?
It was for the tour model.
What is it? Is that for?
It's just like a sign-in sheet, like whether you're going, so we can get a feel of how many people are going.
Okay, you know where it's at?
No idea. It started on this end, so it's probably over there somewhere.
Like 6.
For what? Yeah, no, it was at 6. He just the sign-in sheet.
Okay. So again, I repeat myself, the way the book present the problem for hydrostatic is a little different. A lot of formulas being used. But at the end of the day, it's very similar, right? So I just wanted to be aware of that. Okay. Can you see in the back? Good. Okay. So we have spent a good 2 weeks on differential analysis. Not to mention prior to that, a month and a half ago, we also looked at, by way of the Bernoulli equation, how a differential equation of Euler in streamline coordinate can be developed from first principle, meaning F with MA. Now I want to just put it all together for cohesiveness, so you can see out all the codes in the circle. And this is what this handout is about. What I mean, first, the concept of total acceleration that consists of local and convective acceleration. Any question on that? It's very particular to fluid, that even though it's time steady, you can still have acceleration due to the convective component. No question. Okay, very good. Then we use a very basic differential analysis, like we did with the streamline Euler equation. by drawing a differential element of dx, dy, and looking at quantity theta and so forth, and see how we change across a differential distance, we derive the differential equation of continuity. Can you do that? Can you do that in 3D? Do you understand what this term is about? What does it account for? Say it again?
Change in density.
The unsteadiness in the problem, in this case, by way of the change in density with respect to time. If it's steady, it's gone. And if it's 2D, can you simplify it? And that will be your homework for the inclined plane. Any question on this? So that was the building block. We spent enough time to go through from first principle of theta plus delta theta and all that, just so that you see for once how this equation come about. Any question on that? Can you do that? If I ask you to. Okay, very good. Now I want to strip it down to the bare bone, whereby instead of 3D, I have now somewhat reduced it. Euler, which is inviscid equation of motion, which based on the derivation we see very, very casually on the basis of this approach of differential analysis. Instead of theta for continuity, now we have theta for momentum. I have a two-dimensional x-y coordinate, Cartesian coordinate differential equation. And if the coordinate is oriented traditionally, like x in the x-axis, y vertical, gravity pointing down, that equation look like this. So this is a very special case of the 3D Euler's equation, which is what we have looked at prior to Thanksgiving break, in a somewhat stripped down version. Any question on that? Okay, now you can draw a parallel between what we have done a month and a half ago, again from first principle, for a steady inviscid, just like